Hello, I'm Dmitry Kazares, and welcome to my talk. I want to thank Hojo for all of the organizational work and you for watching this lecture. I encourage you to ask any questions. I think that at any level, formulating a question will enhance your learning from this lecture and will make watching it more worthwhile. Let's get into it. What I want to talk about today contains joint work with a number of people, in particular, Professor Hugh Bray, graduate student Ben Hirsch, and Yu Zhang, and Professor Marcus Curie, and another postdoc, Daniel Stern. I also encourage you to watch his lectures as well. Okay, so one of my main interests and one of my motivations for engaging in these projects is to try to understand the scalar curvature of the Riemannian manifold. Geometrically, metrically, topologically, what are the implications of knowing something about scalar curvature to the underlying manifold? There's a lot of interest in this, and it's a very interesting old problem. And by now there is a real zoo of techniques related to studying scalar curvature of Riemannian manifold. Now, what I'll talk about today is the three-dimensional positive mass theorem in general relativity. And one of my main interests in this is that it is kind of central in that it's a meeting point or watering hole, as I've depicted here, where all the different techniques for studying scalar curvature, the subtle invariant of Riemannian metric, come together. That makes this a nice setting to compare all of these different techniques and try to gain the most understanding of what's going on, of what the scalar curvature says about the underlying Riemannian manifold. That's my interest. Okay. So let's fix the setting. What do I mean by positive mass theorem? Well, let me give you a quick rundown of what is going on here. So in general relativity, Einstein's theory of gravity, spacetime is modeled on a Lorentzian 4 manifold. So that's a 4 manifold equipped with a a definite metric of signature 3, 1. So 3 positive directions, 1 negative direction. I'll give you an example in a moment. So a spatial hypersurface in Lorentzian 4 manifold inherits a Riemannian metric, and also it inherits a second fundamental form. It's a metric 2 tensor on M, which reflects the difference between the connections on the ambient manifold and the hypersurface, reflecting how M is curving in N. Okay, so we would call, if you forget about the ambient Lorentzian manifold and just look at a hypersurface with the induced Riemannian metric and second fundamental form, you can consider that data by itself. You would call that an initial data set. Initial data, the word initial is coming from, you would think of this as a initial data that you specify for the Einstein equations to solve them forward in time and kind of evolve the universe, if you will. Okay, so these are a fundamental interest. Okay, so on the initial data set, you have two quantities of interest, of physical interest. The energy density, this quantity here, where R is the scalar curvature, capital K is the mean curvature of M, the trace of the second fundamental form, and then this, minus the norm of this. there's this other interesting local quantity. By local, I mean it's defined, point-wise quantity, J, which is a one form on the manifold, which is the divergence of second fundamental form minus the differential of the mean curvature. Now, in general relativity, one doesn't study just an arbitrary Lorentzian manifold. Not all Lorentzian manifolds would be considered as a model for spacetime. You restrict those. You restrict your attention to those Lorentzian manifolds which satisfy a dominant energy condition. Okay, so if the Lorentzian manifold satisfies this condition, which I haven't tells you exactly what it is, but if the ambient manifold satisfies that, then the initial data set inherits a condition, which we also call a dominant energy condition, and it is expressed by mu greater than or equal to the norm of this one form J, dominant energy condition. If you happen to have a initial data set with vanishing second fundamental form, so for totally geodesic with k equals 0, the dominant energy condition degenerates to the condition that the scalar curvature of your initial data set is non-negative. Okay, this is the fundamental connection to scalar curvature. Okay, so we should understand carefully the flat spacetime, Minkowski spacetime. Okay, so it's given as a as a manifold. It's R4, R cross R3, where I'll call T the coordinate on the first factor, and the Lorentz metric is given by minus dt squared plus the flat metric on the R3 piece. Now, what are some typical examples of initial data sets within this spacetime? Well, you can consider the constant time slices, where this t coordinate is constant, for instance, t equals 0. You'll recover flat space here. So I've drawn in red. Okay, so R3 with the flat metric would be considered one of these initial data sets. Also, if you have a function on R3 with its differential being strictly less than 1, then you can consider its graph. Well, that's actually too dramatic already. Differential should not be too large. Okay, so this would be the graph of f. And this would also be a spatial initial data, spatial hypersurface of Minkowski. So also you can consider it as initial data set with the induced metric and the second fundamental form. The condition that the differential be of norm less than 1 means that it never becomes null. Another interesting hypersurface, Riemannian spatial hypersurface of Minkowski, is the hyperboloid, defined by the equation, kind of the norm of a vector in Minkowski space, which has length -1. Or we could say defined by the equation t squared is equal to 1 plus r squared, where r would be the radius in the R3 component. Now, the induced metric here turns out to be the hyperbolic metric, the metric with constant sectional curvature -1. And the second fundamental form of this hyperboloid is equal to G itself. So the umbilic hypersurface Minkowski. Okay, these are fundamental examples. So to start our discussion, to start stating our first theorems, let's consider which is historically how things got off the ground, kind of a toy model, you could say, which I had mentioned before, the totally geodesic situation where the second fundamental form vanishes of the initial data set. So in this case, the real data is just a 3-manifold with a Riemannian metric, which should satisfy scalar curvature greater than or equal to 0. Now let's also simplify the asymptotics, or fix the setting that we're going to discuss. So let's suppose that our initial data set has a single asymptotically flat end. So asymptotically flat is what AF stands for. Now, what does that mean? Let me tell you. Well, that means there is a compact set, K, where all of the more interesting topology and geometry of M is concentrated. So it would be this whole under area here, K, so that when I remove K from M, so M minus the set K, there is a diffeomorphism, phi to R3 minus a ball. So there's a diffeomorphism here to R3 minus a ball. So that, and this would be a kind of a coordinate chart of the asymptotic end of the manifold. And the asymptotically flat condition is that in this coordinate system, that's defined by this diffeomorphism, G minus the upper star flat metric decays rapidly as one leaves the manifold and tries to exit the asymptotic end of the manifold. So this behaves something like big O 1 over R, and so do the derivatives. So the derivatives of G behave like 1 over R would behave, so it's big O 1 over R squared, and same with the second derivatives. Okay, so that is the the second derivatives behave like 1 over R cubed. So that is a there are more general definitions you can make, but that's the asymptotically flat condition, the most basic type. Okay, so this is a little bit of a precarious situation we have. We have a 3-manifold, which is positively curved in some sense. Scalar curvature is non-negative, and it has to be transitioning to a flat metric. Not exactly, but it just has to be converging in some sense to flat metric, the Euclidean metric. That's the setting that we're fixed in. And it's slightly precarious because something positively curved has to transition off to something that's flat. And there is a fundamental geometric invariant, which is also physical, which encaptures this tenuous relationship between being positively curved and very close to flat. It's called the energy, or in this toy model is the entire mass of the initial data set, meant to articulate the total amount of mass contained in this gravitating system. Okay, it's given by the following strange quantity in terms of first derivatives of the metric. Okay, so you make this sum and you integrate that over a sphere of radius r. So here is the manifold that we're interested in, M, and we have these spheres, coordinate spheres defined by the chart in the asymptotic end, SR. It would be phi inverse of, literally the vectors in Rn, or of R3 of length 1, or length R. Okay, so you compute this integral. And then you do this for every R, and you take a limit as R goes to infinity. That turns out to be a geometric invariant under a suitable situation. The scalar curvature is integrable, and this asymptotically flat condition. Okay, there's another, so it seems kind of mysterious. It comes from a Hamiltonian formalism for general relativity. It makes some physical sense to call it total energy of the system. Geometrically, you can also think about it in the following way. So remember, we're interested in scalar curvature. That's how I started out this talk. So you have the space of Riemannian metrics on M, big space, and there is a map which takes that to a smooth function on your manifold, which is scalar curvature. So metric is sent to scalar curvature function. Somewhere in the Riemannian metrics on M, say minus K, is the flat metric. This is topologically R3 minus the ball, so the flat metric lives in this space. But on the other hand, you have the metric that you are interested in, that you have, part of your initial data, G. So this defines for you a symmetric 2 tensor, the difference. You're taking, so you can go from the flat metric in the direction of the metric defining the initial data set, G, and you plug that into the differential of the scalar curvature map. You integrate this quantity over your manifold, and that is an interpretation for what this energy is. Okay, rather subtle geometric variant of the initial data set. Now here's the theorem that I've been mentioning this whole time, the positive mass theorem, the Riemannian positive mass theorem. So this is supposed to be interpreted as the mass of the initial data set, the total mass it contains. The theorem says if the scalar curvature of your manifold is greater than or equal to 0, so if there's somehow non-negative matter content, then the total mass of the system should be non-negative, physically reasonable statement. Moreover, if this mass, you could also call it energy, is the same thing in this toy model, is 0, then the only way that can happen is if you're flat. The entire manifold is flat R3. And then many other proofs have come about. As I said, this is a kind of a meeting place for a lot of different techniques and tools in the study of this condition, scalar non-negative. We'll talk a little bit about these techniques as we go on. Okay, so let me introduce my contribution and the contribution of my collaborators. So first, let's give another proof of this theorem. So if you watch Daniel Stern's talk, which I encourage you to, he may explain some greater details to the idea that I'll present here. In your asymptotically flat manifold, you have some coordinates, xi, which take you to, this is M, this is R3, minus a ball. Okay, so fix some coordinates, x1, x2, x3, x, y, z. Okay, and now fix some linear function of those, some linear combination of those things. Or we just think of like just the function x, or x1, say, on your manifold. Okay, I'll explain this business about mx, the exterior region, in a moment. But for now, let's just think about the situation. We have this linear function on the manifold, asymptotic, you call it asymptotically linear function. And here's a statement. First of all, you can find a function which is harmonic in the kernel of Laplace operator using your metric G, harmonic function, unique in some sense, up to addition of a constant, which is asymptotic to this given linear function, given coordinate in the asymptotic end. However, okay, here's the main theorem, main fact, is that the mass, which I was also calling energy, but the mass of this, your manifold, your symmetric, your totally geodesic initial data set, can be bounded below by a integral quantity. This is a bulk integral quantity. Okay, so just to draw you a little picture, here's your manifold M. You could have lots of topology, could have boundary as well. And by exterior region, I mean you cut off a portion of the manifold. And the exterior region would be what I'm highlighting in orange right now. It contains the end of your manifold and maybe remove some interior piece from the initial data set. Okay, so this is the domain of the harmonic function that we're describing here. And here's the following bulk integral, which is a lower bound for the energy. Again, we're interested in a lower bound because this energy, this mass of the system, is supposed to be non-negative. The scalar curvature is non-negative. We're interested in finding the lower bound for this total content of the system. Anyways, okay, so it's given by this integral. The Hessian of the harmonic function, norm squared, divided by the norm of the gradient of the function, plus norm gradient times the scalar curvature of the underlying manifold. So in particular, if the scalar curvature is non-negative, the right-hand side is for sure going to be non-negative. In fact, it's probably positive unless the Hessian of U vanishes. Okay, so you immediately recover a proof of the positive mass theorem, Riemannian positive mass theorem, this way. This is, by the way, joint work with Hugh Bray, Marcus Curie, and Daniel Stern. So this is a new formula for mass. The idea being, for any initial data set, there's some canonical object you can associate to it, some solution of some particular differential equation. In this case, the harmonic, the Laplace equation. And this solution contains information about the geometry and topology of the underlying manifold. And this is one way, that's the general strategy, and this is one way it's plays out. Let me remark that it also holds in some other common circumstances that you'd like to consider, like you might like to have minimal boundary. Maybe the manifold you're considering is not complete, but it has boundary components. In which case, under a minimal boundary condition, one also gets a proof by imposing a Neumann condition to the harmonic function. So you get the same formula. Okay, let's move along. I'll put this into some context for the other proofs in a moment. But okay, so let me just give you a very brief idea of what is the idea of the proof for this theorem. How do you prove the positive mass theorem in this way? Okay, you find this harmonic function, which is asymptotic in some sense to coordinate. Okay, so you find this function. It roughly looks something like, this is your manifold. Then the graph of your function would look something like this of U. It resembles like a plane with slope 1 as you go out to infinity, and does something harmonic in the interior of the manifold. Okay, so you can solve this. Barnick basically did this already. He definitely did this. Now the idea is you compute the Laplacian of the norm of the gradient of your function. That will be a good thing to do. In fact, you'll want to be integrating that. Okay, so why do we want to compute this? Well, let's take a look. You compute the, generally there is a good reason to compute the Laplacian of some section of a bundle that is geometrically important for your manifold. So like the Laplacian of a vector field, Laplacian of a one form, Laplacian of a spinor. This is a good thing to compute because it will contain the curvature of the underlying bundle, which reflects, will contain some piece of the curvature of the manifold. Okay, and let's see how that plays out here. So you compute what this is. If you're familiar with the Bachner formula, it will compute for you the Laplacian of the norm squared of the gradient of a harmonic function in terms of its Hessian and its Ricci curvature of the underlying, Ricci curvature in the direction of the gradient of your harmonic function. So what I've highlighted in orange here is the Bachner formula. Okay, now what is the idea? Well, remember that the gradient of your function divided by the norm gradient of the function, that's a vector field in its unit length, wherever the gradient is non-zero. A regular level set of the function, sigma t, which is a shorthand notation for the set of points where u is equal to t, the level set corresponding to t. Okay, yeah, so for instance, in this toy picture I drew up here, you have this going on here, and then you have gradient u divided by norm gradient u. Okay, so you can interpret that as the unit normal to a level, to a surface in your 3 manifold. Now, remember that if you restrict the curvature of the ambient manifold to a submanifold, you can express the parts of the curvature in tangential directions in terms of the curvature of the submanifold. And this is called, Gauss or Gauss-Guadazzi equations. And in particular, they say for a hypersurface that the scalar curvature of the ambient manifold is the scalar curvature of the surface up to the following: the Ricci curvature in the direction of the unit normal to your surface, plus things that have to do with the extrinsic geometry of the surface, the norm of the second fundamental form, write that as a squared, minus the mean curvature. It turns out that this stuff will cancel with this stuff, and in the end, you're left with something of this sort. You have the Hessian, you have the ambient scalar curvature, and then you have the Gauss curvature, or the the scalar curvature of the level set. And just to see what because you're multiplying, or you're dividing by the norm gradient of u. So what you'll get when you do this integration is something like from the minimum values of u to the maximum values of u over this domain that you're integrating over, and then integrating then over the level sets of your function, just the Gauss curvature, the ways in which the iterated integral differs from the bulk integral is by the norm gradient of the defining function of the level sets. Okay, now we're in a position to apply Gauss-Bonnet to that interior integral to recover, 2 pi Euler characteristic of the level set. Okay, this is the idea of Daniel Stern to do this whole thing I described here. Okay, so what is the context that we're in? Remember, we're looking at an asymptotically flat 3 manifold. Okay, and now we are integrating over some omega. The Laplacian of the gradient of u. Now there are 2 interesting terms that we'll get. So, on one hand we'll get, Hessian squared gradient u plus that stuff. We already know that should be there, so that's not so interesting. That's the right-hand side of the desired inequality. Now what is left over? What is on the other side of the equation? Well, we integrate by parts, and we get the the normal derivative of the gradient of u just from integrating this by parts. Okay, interesting. We have this quantity here, and now it's it's not totally clear what's going on with this. U, it looks like a coordinate function, say like x, plus lower order terms. And so its gradient So the norm gradient of u looks like the norm of gradient x plus lower order terms. This is like roughly on the order of 1 plus a little bit of error. 1 plus first order expansion of the metric, you could say. And so when you take the normal derivative of that, so the normal derivative, the gradient of u, this normal derivative of 1 plus first derivative g, so which is of order r to the minus 1. This looks like 0 plus something which is order r to the minus 2. And you're integrating that over the boundary of some domain. So that's a two-dimensional integral. If you're integrating over large balls in the asymptotic region, then this will, the boundary will look like a sphere. So that'll be on the order of, so the area, the volume, the area form of that boundary will be of the order r squared. And so you're looking at something which is r squared times big O r to the minus 2. So this is something which won't go to 0 necessarily as the regions exhaust the manifold. That's the point that I tried to make. Is that the order of this term is such that it may give you a number if you take the limit as you take the omegas to exhaust the manifold. And it will converge to mass, is the point. On the other hand, you also get a little bit of a difference. So on one hand, you want to use Gauss-Bonnet on the portion of a level set which lies inside of this region omega. This, you would call that sigma t intersect omega, many of these level sets. You would like to calculate their Euler characteristic. Well, you have Gauss-Bonnet for a surface with boundary. That tells you if you take the total Gauss curvature plus the total geodesic curvature of its boundary, since it has a boundary, the boundary of the level set, that's the Euler characteristic. It's 2 pi the Euler characteristic. Okay, so when we wanted to exchange this Gauss curvature term for Euler characteristic, we needed to introduce geodesic curvature. So that's why what I've written here is the kind of the boundary term, you could say, after you do what I just described. Okay, now if you assume, or you know for some reason, that the Euler characteristic of this portion of your level set should be 1, just like, say, a disk. Euler characteristic of a disk is 1. That's what you would expect in the typical example of planes in R3. Then you expect that these two things to almost cancel out. Because for each t, the integral of the, so here's a little picture of what sigma t would look like, sigma t. Sigma t, as you go very far away into the asymptotic region, will look very much like a plane. Because the function is approaching coordinate function x, level sets of coordinate function are planes. So you expect that the level set geometrically resembles a plane at spatial infinity. So you expect that the integral of the geodesic curvature to be close to that of a disk in R2, which is 2 pi. So for each t, you expect this integral, as you go out to infinity, to get very close to 2 pi. And that's true. However, it does not do that in a uniform way in T. So for each T, you look at these level sets, it really does look like a plane. But the way in which it does that over all the level sets, it's not in a uniform way. So this inside integral, it does not really converge to 2 pi times the min and max of u over the level set, over the region you integrate. So when there's some like partial cancellation here, and it turns out that this other term, as you take omegas to exhaust your manifold, so remember, we freeze an omega, we do this calculation I just described, you get this inequality that is now quite messy, but you get this inequality. On the left-hand side, you have these two quantities, which are somewhat tenuous. They both could converge to something non-zero. They almost go to zero, but you can't quite say that they go to zero. And in fact, they converge to mass, the mass of the manifold. And to see that, you have to do some detailed calculations that aren't exactly appropriate for this context. But nevertheless, you can see. You always have to do some work if you want to prove positive mass theorem. There's always some significant calculation, and that's what goes on here. So you can say that the level sets of a asymptotically linear, remember the anti-asymptotics were important here. The fact that u was x plus something else was important. Because as you know, otherwise, if you didn't, well, yeah, it was important to see that the thing that you're integrating here in the boundary term could actually converge to something non-zero. Right? It had to, the integrand here had to grow at a rate of 1 over r squared, so that when you multiply by the volume form of a large sphere, you get something which is bounded and could converge to something. Okay, so harmonic function, which is asymptotically linear. This object contains information about the geometry and topology of the initial data set. Good. And more can probably be done with this. In fact, let's do some more. Okay, so suppose you have let's go to the real, let's graduate from the toy model to the real model. We want to consider inside of a Lorentzian 4 manifold, a 3 manifold, which is spatial. It inherits the Riemannian metric in the second fundamental form. Now there are a number of geometric quantities that can capture the asymptotic geometry of the initial data set. You still have the energy from before, that's the same formula that I wrote already. And now you have 3 other numbers. I goes from 1 to 3, which depend on k. If k is 0, you don't see these invariants, there's 0. But if k is non-zero, then you get some interesting invariants which describe the total momentum of the system, which is naturally a vector. Okay, so now these are at play. And again, well, let's see what we have to see. So the dominant energy condition in this context corresponds to that local energy density being greater than the norm of the local momentum density. And what this should mean is that the total mass of your system is non-negative. Or in other words, that the Lorentz length of the vector E, P1, P2, P3, the energy momentum vector of the system is non-negative. That's the positive mass theorem in the full generality. You would call this the space-time positive mass theorem, you could say. Moreover, if you realize equality in the system, if the total mass is 0, if the Lorentz length is 0, then you should arise as a hypersurface of Minkowski space. In which case, both E and P are 0. In other words, if the total energy momentum of the system is null, if its length is 0, then it actually is 0. It is the 0 vector. Okay, so let's play the same game now for the space-time. Oh yeah, and by the way, let me explain. This is not a simple generalization of the positive mass theorem that I just stated. As you'll notice, there's many fewer proofs of this theorem. The introduction of this second fundamental form, well, it makes it unclear how many of the ideas in the Riemannian setting should generalize. Harmonic functions will no longer do the trick, and we'll have to consider a new operator. So consider, we call it a null space-time Hessian. So given some function, u, you can consider the symmetric 2 tensor, given by the regular Hessian, but then plus an extra term which encodes k. Remember, k is supposed to be the difference between the connection on M and the connection on N, the Lorentzian manifold. That's what k literally is, the difference of those connections. And now the Hessian of a function, that is dependent on a connection, because you're taking the gradient of a vector field being the gradient of u. So you're taking covariant derivative of the gradient of u. You need a connection to define this object. So if you want to encode the tensor k the way in which M is twisting in N, it should enter into the picture, into this Hessian. When you define a Hessian, a Hessian which you want to reflect both the Riemannian geometry and the second fundamental form of your initial data set. It needs to enter into the picture, and here's how we'll say it does. We call this null space-time Hessian for the following reason. Suppose that you are lying, so you have your M lying in some Lorentzian form manifold N. Now suppose you have a function, say u bar, on the entire space N. Imagine you have a function using the metric or the connection from N of u bar, just the usual Hessian, but using the the fact that it's a function on the ambient, on the four manifold. And now you can restrict this object to M. And you can try to write down what is the difference between this object and the Hessian of u restricted to M. Take the Hessian, then restrict that thing, or restrict the function, then take the spatial Hessian. How do these two things differ? Well, you can find for yourselves a formula for how to express one in terms of the other. And you will notice the following. If you have this function u bar on the entire ambient Lorentzian manifold N, which has a null gradient. In other words, if you take the gradient of u bar, measure that with respect to the Lorentzian metric h, it's 0, it's null. Then you try to write down this object, the Hessian, the ambient manifold, in terms of the usual Hessian of the restriction to M. You will get a formula like this. You'll get a formula like this, except this N will have some normal components which you should throw away. So it's kind of like the spatial part of the restriction of the space-time Hessian to a spatial hypersurface. That is what this space-time Hessian is. And we say null because this is under the assumption that the gradient of u bar is null. You have this analogy. Okay, point being, it's just a way of defining a Hessian which reflects the tensor k. Okay, so taking the trace of this space-time Hessian, you get a null space-time Laplace equation. Just take the trace of that operator and set it equal to 0. That's the usual Laplacian plus, okay, now we're taking the trace of the norm grad u times k. Well, that's just trace k times norm grad u. You want this to be equal to 0. This should be the right equation which reflects k. In other words, it's kind of a Laplacian which uses the connection coming from the manifold, the ambient manifold N. Okay, so we should play the same game. We should say, okay, let's try to find a solution to this equation, which is asymptotic to a coordinate, x or y or z. Those should be good canonical objects to associate to an initial data set, which reveal the underlying geometry of the manifold in relation to the total energy and momentum. If we believe in what we're doing. Okay, what is the model, by the way? Well, in Minkowski space, functions that solve this equation, space-time harmonic functions, are a coordinate function plus t. You know, R3 coordinate plus t. The gradient of that will be like partial z plus partial t. The norm of that thing is 0. So those are, you know, those have null gradient, and they are killing for the gradient of these things. The gradient of z plus t, that's killing for Minkowski space. Meaning, if you, I mean, they are the infinitesimal generators of translation in the z plus t direction, which is an isometry for Minkowski space, which means that these vector fields are killing for the Lorentzian metric. What do I want to draw? So here is, say, a graph of some function over t equals 0 slice of Minkowski space. So this could be our M. The ambient space is Minkowski space here. And what would be solutions to this equation? Well, they would just be the restrictions of z plus t to the graph of that function, the restriction of z plus t to m. So z plus t restricted to m is space-time harmonic. In particular, it's actually in the kernel of the Hessian, the space-time Hessian of these things. The restriction of z plus t to a surface will be 0. Okay, so how could you thinking ahead to what we're going to be doing, the level sets of these functions should be important. And what are the level sets? Well, you can consider the level sets as the following. So we know what the level sets of z plus t look like in Minkowski space. There are these null planes. I'm drawing at a severe angle, so it's hard to see. There are these null planes. And then the intersection of these things will be the level sets of the space-time harmonic function, which is the restriction of z plus t to m. These two t's, by the way, they have different meanings. Sorry for the confusion. So you can imagine this process of finding a space-time harmonic function on an arbitrary initial data set and considering the level sets that it gives you, the foliation of surfaces of your initial data that it gives you, is kind of scanning your Riemannian manifold, your initial data set, by null planes, null hyperplanes in the ambient manifold, the intersection of those things to your initial data set. Okay, so it works out. This is joint work with Sven Hirsch and Marcus Curie. So given an initial data set, you can do what we were just talking about. So for some linear function at infinity, some coordinate function, you can find a space-time harmonic function which is asymptotic. So it solves this equation, which is asymptotic to that given linear function. And by the way, you should not consider this on necessarily a general data set, you should maybe pass to some sort of notion of an exterior region. Ask me about that later, and if you'd like to know. So that the energy of the initial data set plus the part of the momentum that points in the direction of the linear function you specified, that will be bounded below by spacetime Hessian, replacing the Hessian in the Riemannian case, plus 2 times the dominant energy condition, replacing scalar curvature in the Riemannian case. And then other than that, the formula looks quite similar. So as a corollary, if the dominant energy condition is satisfied, U minus norm J greater than or equal to 0, then, well, the right-hand side is definitely going to be greater than or equal to 0. So if you apply this formula to particulars, so you need to apply it to the space-time harmonic function U, which approaches minus p at, I guess, well, yeah, at infinity. I guess minus p over norm p. And then you recover the positive mass theorem. Let me also say that this theorem and the Riemannian theorem, they work even without the dominant energy condition being satisfied. These are all new lower bounds for the idiom mass. Okay, now let me tell you something about how this compares to other proofs of positive mass theorem. So let me make a comparison to Witten's proof of the positive mass theorem. So Witten also proved a similar theorem. Not the same theorem. I would say that ours is a little bit stronger, in that it gives you a lower bound for the idiom mass, even without the dominant energy condition being satisfied, which is a relevant feature of the theorem, which does get exploited in later works. Regardless, it resembles Witten's proof. Let me give you an idea about Witten's proof. So Witten uses spinors, which are certain fields that exist on your manifold. Let me just tell you quickly, in case you're interested, what's going on there. Okay, so you have your Lorentzian tangent bundle. You can restrict that to M. Just consider the tangent bundle of the ambient manifold restricted to M. Only consider it over the points which lie in M. This is a Lorentzian vector bundle. Comes with the Lorentzian metric H. And it has a structure group SO31. The isometries of Minkowski space. There is not the isometries, but the origin fixing isometries of Minkowski space. Now in this dimension, this has the structure group has a reduction to the spin 3-1, which is doesn't always happen in general dimensions. It happens in this dimension, and so you can consider instead of just SO31 acting on this bundle, you can consider spin 3-1, or which is isomorphic to SL2C. So happens, 2 by 2, unit length determinant, or invertible linear maps from C2 to C2. Okay, SL2C acts on C2 matrix multiplications, if you like, and so you can consider the product of this tangent bundle with C2 modulo the action of SL2C on both of these objects. This is the spinor bundle. It's a rank 2 complex bundle over the manifold M. I want to consider it over M. Okay, it's a trivial bundle, by the way. It'll just be so it's really just, it's isomorphic to M cross C2, but it has certain algebraic properties that you want to remember. Okay, so a spinner, a section of this bundle, is essentially two complex functions. But that's not so useful. Anyway, so this bundle, sections of this bundle have a very significant operator, the Dirac operator. You form it, it's a first order operator, as opposed to the second order Laplace operator. It's first order operator that you get by, in an orthonormal frame, you take vectors EI and you multiply, Clifford multiplication, the gradient using the connection from the Lorentzian manifold, the derivative of the spinor phi in the direction of EI. You sum this over all I equals 1 to 3. That is another spinor, which is the Dirac operator applied to phi. Very important operator, originally described because it's kind of like the square root of the Laplacian in the following sense. If you do this operator twice, oops, Dirac operator on a spinor, you get the Laplacian of your spinor, which you get just by applying the gradient. Yeah, the spinor bundle, it gets this gradient, and you can form a Laplacian out of that. And that's what I mean by Laplacian here. The left and right hand sides of this equation are both spinors. And on a curved manifold, there is an error term. That comes from the curvature. Again, you have a section of an important bundle on your manifold, and the Laplacian of such a thing reflects the geometry of the underlying manifold. And this this curly r here is this term. This is called the Weissenbach formula for this Dirac operator. You get a different Dirac operator, you get a different Weissenbach formula. This is a particular operator, Dirac operator, and notice that it's using the connection from the ambient manifold on sections of a bundle over the hypersurface. So it encodes that K that we talked about before. So you see some similarities. You have spinors that are in the kernel of this Dirac operator called harmonic spinors, Dirac harmonic spinors, you could say. And Witten considered Dirac harmonic spinors to prove his positive mass theorem, much like how we consider an operator which uses the connection from the Lorentzian four manifold, find some canonical objects, space-time harmonic functions, to solve, and then study these objects carefully to relate the total energy of the system to the internal geometry. And Witten does a similar thing. Okay, so he does this whole thing. He looks at these spinors. He solves this equation, requires some work. Also see Parker tabs for more mathematical description of this argument. Okay, and then you look at this formula. By the way, this curvature term, if you pair it with the spinor itself, it's non-negative by the dominant energy condition. So it's practically the dominant energy condition acting on the spinor in an appropriate way. Okay, so you look at this equation. If you plug in a harmonic spinor, the left-hand side is for sure gone because d of it is 0, so that's out of there. And then you integrate this thing over a big domain in your 3 manifold. Domains which you take to exhaust the manifold. You integrate by parts, because on the right-hand side, you have a Laplacian type thing. You integrate that by parts, you get a boundary term. And then, by the way, you can kind of forget about this scalar curvature part because it's going to be non-negative. So it's like how the dominant energy condition appears in the formula that I just presented. Okay, so then there's that term when you're integrating over the manifold. And you also get a, well, let me just write it down. So you get this scalar curvature phi paired with phi. And then you also get gradient of phi squared from when you're integrating by parts. Where you pair the left and right hand side with phi, and then you integrate that thing on the bulk. That is less than or equal to, and it's definitely bigger than or equal to 0, by the way, but it's less than or equal to this boundary term, and then you need to compute the boundary term. You always need to do a calculation if you want to prove positive mass. So you compute the boundary term. And you obtain, oh, by the way, the spinner that you want to find, the harmonic spinner, should be asymptotic to a constant spinner, just like we are finding functions which are asymptotic to a coordinate function. Okay, so on the boundary term, on one hand, you get the energy of the initial data set, and then you get a portion of the momentum, which depends on the phi naught that you chose. There are many different constant spinners, more constant spinners than there are constant vectors, or linear functions. Linear functions, there's basically 3 of them, but a spinner that's like 2 complex numbers, so there's like 4 of them. Anyway, so you get some portion of the momentum which points in a certain direction having to do with the constant spinner you chose. Then you can choose the constant spinner so that this becomes negative the norm of P, and you recover, well, you get the positive mass theorem. This is the first proof of the space-time positive mass theorem, where you have non-zero K. So that's Witten's proof. Okay, there's a lot of, well, let me not go there. Yeah, there's a lot of comparisons to draw with our proof. So you can compare the spinner to d of our spacetime harmonic function. So you compare the spinner in the one form. Remember, du, remember that doesn't require a metric to specify. That's a canonical object you can associate with just a manifold in a function. But the way the connection, the tensor K, enters into the picture, enters into the equation, is when you try to define the Hessian or the Laplacian. So the du is like the canonical object that we're studying in what we do, but we act on it. We find the Laplacian, or adjoint of differential, you could say, which encaptures the twisting of m inside of n. Anyway, so that's the comparison. The spinner should be compared with the one form or the vector field, the gradient vector field you get. Now, if you've heard about spinners before, very interesting objects. I encourage you to learn as much as you can about them. It's an undervalued skill to know something about spinners. No matter what type of geometry you do, it won't hurt you to learn more. I encourage you to take a look at, if you're really interested in this material, in general relativity and spinners, then I would point you in the direction of Penrose spinners and spacetime. 2-volume book about spinners in the context of spacetime. If you had a mastery of that material, few people have mastery over how to do basic things with spinners. But anyway, so if you heard a little bit about them, they are in some sense supposed to be square roots of vector fields and tensors in a very rigorous, real sense. But so anyways, if you have a spinner, you can define a one form. You can square the spinner in a sense. And here's one way to do that. There's basically only one way, but here's one way to do that. You define a one form in your manifold. So suppose you have a spinner. Now they get acted on by vector fields, by Clifford multiplication. You can define a one form in the following way. Well, okay, to define a one form, you need to tell me how it acts on vector fields. So here's how it acts on a vector field x. The one form acting on x is equal to this number, take the action of x on phi, and then pair that with phi using this particular Hermitian pairing here. I won't, you don't need to get into the details here. This is more philosophical what I'm saying now. And now you can compute what does it mean for alpha to be co-closed? So remember, co-closed as something's like, you know, the adjoint of D alpha is 0. Closed would mean D alpha 0. This is the same as like D if star alpha equals 0. This is closed. And this is co-closed. Different conditions. Okay, so if you do this construction with the spinner, and the spinner is Dirac harmonic, then alpha will be co-closed in a sense. Now, if that one form that you defined happens to be the differential of a function, if it happens to be exact, then that function will solve space-time harmonic equation. So if you make a Dirac harmonic spinner like this, like Witten does in his proof, from that form a one form in this way, and then also for some reason you know that that one form can be integrated into a function that is exact, which is an extra condition, but can be arranged for. And then that function that defines the one form will be a space-time harmonic function, solving our equation. So in some sense, so if you have a space-time harmonic function, du will be the square of a Dirac harmonic spinner. So in some sense, this du should contain a little bit less information than a Dirac harmonic spinner because you've squared it and you've kind of lost some information. You know, a spinner is generally a more subtle object than a vector is. However, this is a very peculiar thing. We can actually do something, you know, our positive mass theorem is, you know, a slightly stronger statement than Witten's positive mass theorem. It works in all dimensions, but it doesn't work in all dimensions. It only works in dimension 3, which Witten's works in all dimensions. Ours only works in dimension 3, but it works without the dominant energy condition. And it gives a refined lower bound for the total energy momentum. There's some other advantages, but the thing that I want to point out is that you get this new object, which is the foliation, the level sets of the space-time harmonic function. And that object contains some information that you can't necessarily see from the one form or the spinner itself. So somehow squaring the spinner allows you to integrate that to recover an underlying function, space-time harmonic function. And the level sets of this function are key to our proof. So it's strange that you square phi, only after you square the spinner can you realize that there is an underlying foliation that reveals some geometry of the initial data set. That's the kind of mysterious part of this proof that, you know, we're still trying to understand. So we're still trying to understand that, and maybe let this be a little bit of a lesson if you're a younger student. So we're not proving, you know, the theorems are new, the lower bounds for mass are new, but the conclusions are not wholly novel. You know, positive mass theorem already has a proof, has several proofs. So why are we doing this? Why are we doing what seems like reproving old theorems? Well, first of all, they're new results. They are new lower bounds. Let me be clear about that. But also, we need a deeper understanding. You want to deepen the field, provide some depth to the understanding of how the geometry of the interior of the manifold is affecting the total energy and momentum. and see how the dominant energy condition is affecting the geometry of the manifold. That's the overall goal. And so we need to consider these ideas carefully. How do you consider an idea carefully? Well, you see how it behaves, what that language tells you about various phenomena. Okay, so we just considered what is called asymptotically flat space-time positive mass theorem. Let's consider a different context. See what this language that we're making can say about some other phenomena. Okay, now let's take a look at the hyperboloid in Minkowski space. If you have Minkowski space, you have this hyperboloid, which, as we mentioned, was asymptotic to hyperbolic space, sectional curvature -1. Now we know what the right equation, we know what the equation that we want to study is. The space-time harmonic should be solved by the restriction of z plus t, or minus z minus t in this case, to a spatial slice, spatial hypersurface of Minkowski or any other space-time. So it takes kind of an interesting form on the hyperboloid. Hyperboloid is very different than the t equals 0 slice. On the hyperboloid, you can write this function as negative square root 1 minus r squared. So here the r is in the base. This is hyperboloid. And when I say r as a coordinate on the hyperboloid, I'm talking about this r, the r in the xyz plane, the t equals 0 slice. Minus r times cosine of phi, where phi is the the distance on the sphere to the North Pole. The physicist phi. Okay, so this is a very it's a less symmetric looking function than just a simple coordinate function, say z. But this should be our model, because this definitely solves space-time harmonic equation. In fact, it's the model. It has a vanishing space-time Hessian. So this should be fundamental if you want to study hyperbolic initial data sets. Let's take a look at this function a little bit more carefully. So let's take a look at the level sets. So here I draw a picture on the left. By the way, the hyperbolic metric in these coordinates, where r is the distance in the xyz plane, hyperbolic metric can be written like this: 1 over 1 plus r squared, dr squared plus r squared times the round metric in sphere, radius 1. Okay, so if we consider hyperbolic space as this hyperboloid in Minkowski, then the level sets of minus z minus t, they are the intersections of the hyperboloid with null planes. So you get some picture like this. They look like kind of hyperbolas themselves, because you're intersecting, they're kind of like conic sections, except that it's not a cone, you're intersecting a hyperboloid. Okay, so you get these red lines in your initial data set, which is the hyperboloid. They look like this. Notice, by the way, that v only goes between negative infinity and 0. Okay, we can also look at level sets by projecting from the hyperboloid to Poincare disk. So in Minkowski space, I'm zooming in here now. In Minkowski space, you can hyperboloid sits at height z equals 1. That's the very beginning of the hyperboloid, then it goes up from there. Now you can draw lines from a point on the hyperboloid to the origin of Minkowski. Draw these lines. They intersect this disk here of radius 1, centered at height t equals 1. So this defines a projection from the hyperboloid to the unit disk. Under this, so this is the Poincare disk model, where the metric can now be written like this. Basically, a flat metric divided by the square of 1 minus distance from the origin in this unit disk squared. I'm drawing all two-dimensional pictures, but I'm really thinking about three-dimensional objects. Okay, and the level sets of this function, this special function, which is supposed to be guiding us, the model function, are horospheres. There are these little circles that all intersect some given point at infinity. They look like spheres. And as you change the level set, from 0 to minus infinity, then you sweep out the hyperbolic space by these spheres. If you wanted to instead project onto an upper half space, given by some kind of a plane orthogonal to the level sets, that defines another projection from the hyperboloid, as I try to draw here. That defines a projection to the upper half space, in which case the level sets, in which case the metric takes the form 1 over the vertical direction squared times the flat metric, also conformal to flat metric. And the level sets of our model function are planes. Notice that the gradient of this model function is no longer killing, like the gradient of x was killing for Minkowski space, and the t equals 0 slice. Translation in x was killing. Now translation in x in this upper half-plane model, that would be like translating upwards, is no longer killing. But it is conformally killing. So it does not generate a isometry of hyperbolic space, but it generates a map which, after you apply this map to the metric, is not the metric, but it is conformal to the metric. The metric being hyperbolic metric. So now we're trying to push our techniques into this arena where we know we should, if we want to reflect the total energy and momentum of some asymptotically hyperbolic initial data set, now where the geometry is modeled on a hyperboloid at infinity, not on flat space, we should be studying these functions, and they are of quite a different nature to the functions we were studying before. These functions are, their gradients are no longer killing. They're conformal killing, and this creates some complications. By the way, so just to describe what the studying is here, we're going to be studying asymptotically hyperbolic initial data sets. These are manifolds which have a chart to hyperbolic space where the metric decays to the hyperbolic metric, and where the 2 tensor K converges to the 2 tensor of hyperbolic space, which happens to be equal to its metric. So this also makes the problem of a very different nature. Now the K is no longer decaying. It converges to something positive definite. Let's see what happens. So this is now new work with Hugh Gray, Sven Hirsch, Marcus Curie, E.U. Zheng, where we prove a positive mass theorem in a similar sense. So you can push this technique into this new context. The problem is much more difficult now, but nevertheless, you get the following theorem. If you have a asymptotically hyperbolic initial data set. So as I said, it resembles the hyperboloid in Minkowski space at infinity. It's supposed to be modeling like if you have a Lorentzian form manifold, which is asymptotically flat, then these initial data sets should be like hyperboloids in that data set, close to null cones. Anyways, if you have such an object, which is has trivial topology, so in the sense that the second homology group vanishes. Then, first of all, you can find a space-time harmonic function which is asymptotic to these model functions, these VZs, or Vx or Vy functions. So you can solve the equation, which is now no longer trivial because it wasn't trivial before, but it's definitely not trivial now because now the equation has the form Laplace u plus trace k grad u equals 0. That's space-time harmonic equation. But the nonlinear part of this equation, since the norm of the gradient of a function is nonlinear in the function, that doesn't decay as you travel far away from into the asymptotic region, because trace k, instead of converging to 0, like an asymptotically flat case, it now converges to 3. It makes the equation of a very different nature, especially in the context of the asymptotic condition. Nevertheless, the total energy minus the momentum in the direction of the chosen asymptotic coordinate, in the what I wrote above here would be just z, is bounded below by space-time Hessian squared plus mu minus norm j, or more particularly mu plus the part of j pointing in the direction of the gradient of u. That bulk integral, just like before, bounds the what you would call the hyperbolic mass from below. Things get a bit more complicated here. This is forthcoming work, by the way. And these complexities compound in a way that forces us to make this extra assumption of no topology. The no topology condition, just to be clear and to finish the lecture, comes at this stage that we saw quite a while ago, where you need to arrange for this Euler characteristic of these level sets to be less than or equal to 1. Now, this can fail to be the case if you have a level set which looks like this. So in your 3-manifold M, you have a sigma t level set of your space-time harmonic function, which contains some spherical level set. If you have a spherical level set component of your level set, that's bad news, because that Euler characteristic is 2 plus whatever the Euler characteristic of the other piece is, which is at least 1. So then that would be bad news. So you need to arrange for a situation where the level sets will never have spherical components. And one way you can do that is to assume that the underlying manifold has no second homology. And in these other theorems where we didn't have to have that assumption, that was because we could pass to some region where that condition held, this exterior region. I can provide any details on that if you would like. Well, let me conclude there. Thank you very much for your attention. And again, I welcome any discussion, questions, or comments. All right, have a good day.